Welcome back. This is the first of a series of videos on Chapter 9, searching, sorting, and looking at different algorithms for performing these common functions. We're going to start with search algorithms. The purpose of a search is to locate an item within a list, a collection or list of values. And we typically provide either the answer, yes, it is there, no, it is not there, or we will provide an answer that indicates where a particular value is within that collection. Our simplest search is a linear search, which is what we do by starting at the first element of an array, comparing it to the value that we're looking for. The value that we're looking for is called a search key. So when you see the variable key, it means this is the value that you're looking for. And in order to solve this problem, we must walk through the array, element by element, until we find it. Okay? Now, this form of the linear search is answering the question, where is it? So we are obligated to return a subscript that says the value that you want, the search key, is at a certain position. It is possible that the search will not be successful, in which case we still must return an integer, but this integer must represent a value that cannot be a subscript. So typically a negative value will do that. And so as we see, we have our standard for loop for walking through an array. We simply compare each element. If you have a match with the search key, you just return the position where it occurs. Otherwise, we keep repeating the loop. If the loop ever completes, it means you went through the whole array and never found anything, in which case you need to return a value indicating not found. And again, that value must be an integer, which cannot be a subscript, so we use a negative value. Another version of the same algorithm is answering the question, is it there? So this is a Boolean function that says true or false. And it looks pretty much like the one that you saw before, except that we're going to return true or we're going to return false. No cussing. No cussing. Y'all don't see this. Don't need that. Okay? Now, here's an example. If I'm searching for the value 11, I search 17, then 23, then 5, and then 11. When I hit 11, I will say it's at position or subscript 3. If I'm looking for the value 7, I start here, 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 and I must go through the entire array if it is not found. All right? So the question becomes, how much work is involved in this search? Well, it's pretty clear that whenever you have the case where the search key is not found, you must go through the whole array. So if you had an array of n elements, you must do n comparisons. All right? You must do n comparisons. Here is the comparison that we are counting. In the case of searching, the work is typically a measure of how many comparisons it takes to answer the search, yes or no, or to render position. The linear search algorithm is extremely simple, and it follows the same old linear stepping through an array that we're used to. It's inefficient because on average you must go halfway through the array. In the worst case, you've got to go all the way through. So imagine if I had 1,000,000 elements. You can expect it to take 500,000 just to find a typical element on average. All right. Now I think with that we're going to bring it to a halt, and we'll continue with a more efficient yet slightly more complicated algorithm for searching. So we're going to stop here.